Good afternoon. Welcome to our students and visitors for this forum on the situation at the Japanese nuclear reactors. We've assembled a distinguished forum of panelists here: Professor John Lee, Professor Tom Downar, Professor Bill Martin, Professor Designate Annalisa Manera, and Professor Kim Kearfott. And then when all the presentations are finished, then we will entertain questions from the students primarily. So would somebody change the next slide? So first and foremost, we would like to extend our condolences to the people of Japan who are the victims of the devastating earthquake and tsunami. The faculty of the Nuclear Engineering and Radiological Sciences Department stand ready to provide technical advice and assistance to the people and government of Japan. Next slide. So the goals of this discussion are to educate students, the public, and the media, and policymakers to understand the events that occurred at the reactor sites in Japan. And finally, we'd like to learn some lessons from this so that we can move forward with safer nuclear power reactors. Next slide. So this is the outline of the presentations. We'll start out with Professor John Lee, who will give an introduction to the boiling water reactor and the sequence of events in the Japanese reactors.
Good afternoon. As introduced, I'd like to begin with a simple, short introduction to the boiling water reactor systems, and especially focusing on safety features of the power plant, and then try to summarize as best as I can the chronology of the events that resulted in significant damage to some of the units at the Fukushima power plant site. So what I have here as a first simple slide is the overall picture of the BWR system, including reactor core and primary, secondary containment, and some of the safety features. So this is a reactor pressure vessel, inside which is located is the reactor core, and I have the next slide that will illustrate the reactor core itself, and then eventually fuel element. And we have this yellow-shaped, yellow-colored, light bulb-shaped structure, which is the primary containment. 4 to 6 inches in thickness, steel structure, which is reinforced with several feet of concrete. And then that is the primary containment. And then connected to the light bulb-shaped dry well, primary containment, is the suppression pool, which is connected through automatic depressurization system valves, several of them. The idea is when the pressure builds up in the reactor vessel, steam can be vented to the suppression pool, thereby relieving the pressure. And of course, suppression pool itself will be cooled by another heat transfer loop. And the water will be pumped into a reservoir, which I'll indicate in the next slide or two. And sitting outside, of course, here is the secondary containment structure, which is basically robust concrete building, does not have the strength of the primary containment in protecting the release of radioactivity in case of major accident. And of course, this is a structure that was damaged in a couple of the units at Fukushima plant site. And what we have here is this spent fuel storage pool. And we have the crane that moves the spent fuel elements in and out of reactor core into the pool. That is the structure that we have here. And this is maybe 40 feet or so in height. And it's a large pool, but located above the reactor core. Reactor core is located somewhere here. And this is a fuel handling equipment we have. So I'd like to turn to the next slide, which indicate the reactor vessel inside the reactor vessel, reactor core structure altogether. This is the reactor BWR6, some of the larger unit than we have at the Fukushima site, but this is the reactor vessel itself. So what we have here is in the orange colored area are the fuel elements, 12 feet in length. And next slide will show you the actual picture of the fuel elements. So this is 12 feet in length. And we have here at the bottom control blade, as well as some of the instrumentation system that will be driven into the reactor core as necessary. In BWR systems, control rod or control blades, as they are sometimes called, are inserted from the bottom, not from the top. And then above the reactor core here, with the fuel support plate, are two sets of steam separation equipment. First one is a rotating swirl vane system. On top of that is the simply dryer that separates the liquid water from vapor and recycles back into the reactor core through this path, the annulus path that exists between reactor vessel, shell, and the steam separator equipment. That is the basic structure of the reactor vessel. Again, this is an illustration of a reactor core and vessel larger than what we have at Fukushima site. Next, I thought I should zoom into the fuel elements to give you some idea on what we have. So this is, again, somewhat of a larger fuel elements, perhaps older fuel element, in this case larger, but fuel element than for the Fukushima site. And what we have here are 4 fuel elements, each one of which contains, in this case, 8 by 8 array or lattice of 12-foot long fuel element. So each one of these fuel rods are 12 feet long, maybe about ½ inch in diameter. And each one of these fuel rods is bunch of fuel pellets loaded up into thin zirconium alloy cladding. And this zirconium cladding played an important role eventually in the evolution of the accident. I would say the event is a station blackout event for the reasons that I'll describe in a minute, rather than a pure, simple accident. And what we have also here illustrated is cruciform-shaped, cross-shaped control blades that are inserted from bottom of the core into the lattice of the fuel assemblies we have. So now I have schematics of the safety systems that exist at Fukushima site. This is, again, Mark I containment, as is discussed in the media. And what we have is a reactor vessel here. And again, we have looked at the reactor core inside here, and fuel element, 4 fuel elements with a control blade structure illustrated. And this is the primary reactor vessel in the shape of light bulb. And this is steel lined, 4 to 6 inch steel. And outside of this steel shell is concrete, reinforced concrete of 4 to 6 feet, I believe, in thickness. And this is the cutaway view of the separation pool. And this illustrates vent valve, automatic depressurization system valve that to relieve steam that builds up inside reactor vessel. So there's a connection here that is not shown, okay? And we have here a number of safety systems, but what played a role in the evolution of the station blackout event at Fukushima site is this pump here, which is called reactor core isolation cooling system pump, which is steam driven and which is part of the residual heat removal system itself. And as many of you know, even after reactor is shut down and fission reaction is terminated due to the radioactive decay of many of the fission byproduct, heat is produced, and we need to keep the reactor core covered and cooled. That's where the residual heat removal system comes in. And here's the pool of water that served as the reservoir for the reactor core isolation cooling system pump. And this system works such that even when electric power is lost, it can pick up suction through the steam that comes out of the system and be able to pump water from condensate storage tank back into the sprayer or spudger inside the reactor vessel above the fuel element. So that is the idea behind this passive, in some way, or backup cooling system we have in this particular kind of power plant. So let me quickly go through the sequence of event following March 11 earthquake of magnitude 9.0 combined with the 12 feet high tsunami. So as soon as the earthquake hit the site, reactor scrammed, which means the fission reactions were terminated within seconds of the earthquake. And together with that, turbine systems, which are connected to electric generators and produce electricity, also tripped almost immediately. And so again, the important point is fission reactions terminated. And as a backup system, emergency diesel generator came on. And it provided cooling for about an hour or so. But another wave of tsunami hit. And apparently, fuel supply system were either knocked off or blown away. And diesel generators stopped working. That's when this steam-driven backup pump came on, RTIC pump came on. And again, it was able to use steam that is still produced from the reactor core and pump condensate storage tank water into the reactor vessel. And the steam would be produced and then would come out into the the separation pool. And that was the heat transfer path. And there was another heat transfer loop that would take away heat from the separation pool itself that I mentioned. It's called isolation condenser. But something like 12 hours after RTIC pump came on, one of the valves, I don't know which one and where, stopped functioning due to the discharge or depletion of the battery that was required to have the valve functioning. So that's when we lost the cooling capability. So up until that time, although when diesel generators stopped functioning, we lost station power, and that's known as station blackout event. And so the way I describe the whole sequence event is due to the earthquake, the plant suffers station blackout event. And the backup steam-driven pump worked for about half day. And then due to tsunami and the other events of nature, we lost the cooling capability. So within several hours to a day, I do not have the exact sequence, there was overheating and uncovering of fuel element. As a result, the zirconium cladding reacted with water, and it's an exothermic reaction that produces hydrogen. So pressure built up inside the reactor vessel, and some of the hydrogen mixed with the steam was vented into suppression pool. And again, pressure is building up here. So there was a relief valve, which is not shown here, was manually opened, and the hydrogen was vented into the space that's outside of primary containment, which means that space is inside the secondary containment concrete structure. And hydrogen ignited, if you will, chemically reacted with oxygen, air in the secondary containment space, and that knocked off the rooftop of Unit 1 and Unit 3, I believe, of the Fukushima plant. And that was the beginning of the deterioration of the event. And of course, the uncovering of the reactor and the core continues on and off. And that's when the Tokyo Electric Power crew started pumping seawater through fire engine, fire hoses, and so on into the reactor vessel. And this mode of emergency cooling was considered and included as a way of handling emergency situation like this. So it was not something that they came up with in the last minute, but was in the technical specs and operating procedures for the plant. So effort was made, and effort is still continuing to keep the damaged reactor core under cover and cooled the way I understand. So again, the hydrogen escapes through the relief valve that was manually opened. And right now, the way I understand, certainly some of the units, maybe Unit 1 and Unit 3, have a large fraction of the fuel elements damaged. But under some amount of water, so I don't see the imminent danger of complete fuel meltdown of any one of the 3 units of the Fukushima site. And based on our experience with the unfortunate accident of 1979 at 3 Mile Island, and in that case, 2/3 to 3/4 of the fuel element suffered melting, and yet the pressure vessel did not fail. And subsequent analysis indicated that there is no danger of pressure vessel breach at that particular site, the particular power plant. So if the crews working valiantly can maintain coverage of the damaged cores at units 1, 2, and 3, I believe over some period of time, especially with the offsite power supposedly restored today, if not last night, then we should be able to expect that the cool down, stable cool down configuration of the power plant could be achieved over some period of time. And I'd like to also mention, there will be additional talk, I know more in detail, but the worst exposure to the general public in the case of 3 Mile Island was equivalent to 2 chest X-rays. And so far, our indications are that exposure to those outside the evacuation zone has not been much above that level of radiation exposure. And I'd like to conclude my presentation with the point that all of this aggravated evolution, deterioration of the core and vessel was primarily due to large earthquake that was well beyond the design-based earthquake and design-based tsunami for which these plants were designed. And also because of the long period of station blackout, long period over which station power could not be restored. Those are the primary reason for all these difficulties and deterioration of the events. But today, I feel guardedly optimistic that we'll be able to bring the reactors, all 3 of them, plus the 3 that are on outage, to a safe cool down state over some period of time.
We'll now hear from Professor Thomas Downar.
Well, John already mentioned the importance of the zirconium. So what I thought I would do is go into that in a little bit more detail because the loss of the roof, the secondary containment, was very important for the release of radionuclides. This is a schematic just showing us, the zirc water interaction at about 1200 degrees. And after the hydrogen is produced, then what we're concerned about is this combination of air, steam, and hydrogen in the concentration that can lead to detonation. If we're down here, we're okay. It's when we get into this regime here that we become concerned. Well, this has been something that people have anticipated. And hydrogen detonation prevention mechanisms, first, the inertization by nitrogen. Secondly, and in fact, that one was existent in the primary containment of Fukushima. After that, then controlled combustion of the hydrogen, catalytic recombiners, basically producing water, or spark igniters. The secondary containment, had igniters, but apparently they didn't work. The next few schematics we'll take a look at, in Unit 1 specifically, the mechanisms by which the hydrogen then made its way up into the upper part of the secondary containment. Basically, we heat up the fuel, we start to produce steam. Hydrogen is produced from the zirc-hydrogen interaction. The hydrogen makes its way down into the suppression pools. Now, under normal situations, what's going to happen is we're going to keep the pressure low in the suppression pool by cooling. However, if we lose the pumps, then what happens is we have a venting of the hydrogen, and it makes its way up into the secondary system, the secondary containment up here. Once we're up there, the cooler sealing allows for the condensation of the steam, and that contributed then to the concentration of hydrogen that then made the conditions possible for the hydrogen explosion, and of course then the significant damage of the secondary containment. We've seen these pictures a lot on television, the before and the after. So this is a hydrogen explosion. You know, the big concern is that what's happening now is we're seeing that the spent fuel pit is also had a hydrogen explosion. Secondary fuel pit is already part of the exposed to the secondary containment. So the buildup of hydrogen there has led then to, in Unit 4, the exposure of the fuel to the environment. This is summarizing the 6 BWR units, and I'll show you a slide in a second, the status. Unit 1, 2, and 3 were in operation. Unit 4 was down for an outage. The bad news is that that means the fuel was in the spent fuel pit, which was then only exposed to only contained by the secondary containment system. So this slide, which I think is one of the best updates I've seen, is on the JIF website. And it's very busy, but if you go to the website, you can see it. But you know, red is severe, yellow is high, and then green is low. But what we want to do is just look at the red. And here you can see building integrity. So that's where we had the hydrogen explosions. You can see in Unit 1, 3, and then, of course, then, as I've mentioned, in Unit 4, even though the fuel was not present in the reactor, it's the spent fuel pit here, you know, that has been the cause of the problems. And this is where now the efforts are underway to keep the spent fuel covered. So that's, you know, just a kind of a synopsis of the hydrogen explosion, where we're getting the hydrogen from, and then what are the mechanisms by which it's possible that we've seen the explosions. So next, I think, Bill, we're going to talk about potential for recriticality.
Okay, so oops. Can you hear me okay? Okay, so 4 days ago, I was emphatic in saying that that recriticality was not possible in the reactors. And that's still true. And that comparison of this accident to Chernobyl was simply not useful and sensationalist. I think I have to back away from both of those a little bit. So I'd like to try to explain that. And I know that there's my hesitancy in saying this is I don't want to see myself on the news saying that this is going to happen. So this is what my best judgment is to this point, without a lot of information to inform me. Okay? So let me try to go through this as best I can. So I'd like to just draw a comparison with 3 Mile Island and Chernobyl, just to get a sense for the magnitude of these accidents. So as Professor Lee said, 3 Mile Island, there was substantial fuel melting, maybe 2/3 of the fuel. It was a small LOCA, loss of coolant accident. There are huge differences between these accidents. This accident is entirely due to a natural disaster. 3 Mile Island was a combination of equipment failure and human operator failure. I think Chernobyl can be given entirely to operator and procedure errors. So there's huge differences in what caused the accidents. But what we're worried about when the accident occurs is the consequences. And so in the case of 3 Mile Island, it's a relatively minor release of radiation. There was a release, but it's relatively minor, equivalent to a couple of chest x-rays. And the key was sufficient cooling water was forced into the core to keep the fuel cool. That was the key. And that's the key now for Fukushima. The challenge for TMI-2 and the Fukushima reactors was removing the decay heat power. It's important that you realize that the reactors were shut down The fission chain reaction was terminated immediately. And it's only decay of radioactive products now that's causing the decay heat. The same stuff that we use to power spacecraft that are exploring the outer solar system. It's decay heat from radioactive sources. TMI is classified as, you may have seen this, so I'd like to explain this briefly, as INES level 5 accident. And next one. So it's like a Richter scale for nuclear accidents. So 1, 2, 3 are just sort of not real serious. They don't call them accidents. 4 is an accident, which is more serious. But each one of these is about a factor of 10. And this is very qualitative, as you might imagine. But a factor of, like, we don't have meters that tell you, oh yeah, this is a 4.5. So we have, but TMI was a level 5. So just to stick it in context, a level 5, which means accident with wider consequences. So wider consequences means that it's beyond the boundary or of the plant itself. So, and it did. There was a radiation release well beyond the boundary of the reactor. So, accident with wider consequences. A factor of 100. This is qualitative. I could argue 1,000. That was Chernobyl. Chernobyl was a 7, sort of like the worst that could happen. So you might ask, where's Fukushima? And we don't know that. I think it's somewhere above a 5. It's just been recategorized, I guess, as a, well, somebody help me now, 4 or 5?
6 according to the IAEA, 5 according to the Japanese government.
Okay.
Between 5 and 6.
So between 5 and 6, okay. And that's reasonable. The best that can happen right now is the 3 Mile Island endgame. That's the best. What else? What could be better than that? And that means that all 3 reactors are cooled down and we resolve the issues in the fuel pits. That's a TMI endgame. And there's probably even more radiation release, although we don't know that yet. But saying it's more than 5 is probably okay. I can't argue with that. Okay, Chernobyl, totally different kind of accident. It was a prompt supercritical power excursion. And Google that, you'll find out what that means if you're not a student in this department. Within a few seconds, the power increased by a factor of 1,000. It was at 20% power, and so it went a factor of 1,000 times that. Didn't last very long because it just blew itself apart. The heat was deposited, it boiled all the water away, the water steam explosion in the end, and it blew the top off the reactor. 1,000-ton top. But aggravating it, and actually what's caused all of the most, well, not all of it, but a huge chunk of the radiation exposure is the fact that there was a 10-day fire, the 2,000 tons of graphite, which is the moderator. This is an unusual reactor, a boiling light water graphite moderated reactor. And it had a dual role. It created plutonium for weapons, and it generated electricity. This reactor was on the ragged edge of stability, and the operators put it over the edge, and it went up. It had no containment. There's no containment in these reactors. I'm not sure if containment would have helped when you can blow a 1,000-ton cover off the reactor, but still there's no containment. It was an ideal, and you had this fire, very hot fire, according to Professor Fleming, that was blue hot fire that was enough to to vaporize solid fission products, which normally would just stay in the reactor, like certainly at 3 Mile Island or Fukushima in the reactors. They're not going to go anywhere. It vaporized them and put them up 40,000 feet up in the air and was able to transport itself around the globe. This is a perfect mechanism for distributing fission products from within the core. This is like a 10 on that accident scale. I mean, this is certainly a very severe accident. Okay, so this is the other thing I said couldn't happen. And I still believe that for the reactors. And that's because the geometry, when you start thinking about fuel melting, and we don't know what's going on inside this reactor, but 3 Mile Island, there was substantial fuel melting. But you're going to get some sort of a pile of fuel. Well, this pile isn't the way a nuclear engineer would design a reactor. It's not going to go critical. You have to have water to moderate, to drive the reactor critical. So there can't be a sustained fission reaction in a pile. That just has water around it. So that's why I believe, certainly, that in the reactors themselves, there's no chance of recriticality. However, we've got these spent fuel pools out there now. And while I have a hard time hypothesizing how would the fuel, I mean, you're talking about racks holding the fuel elements up. We know that in these, when the pool is filled with water, which is a moderator, we need the water for a chain reaction. When you fill the pool, the fuel is not critical because it's spaced. It's spaced apart, and it has boron absorbers throughout the pool. Now you got to start hypothesizing, okay, now we've got, the water's gone away. Well, that's good for criticality, right? It's utterly impossible to go critical. However, the fuel heats up because there's decay heat. This fuel is about 0.1% power maybe in the spent fuel pool. It's been in the pool since December. So it's had a long time to decay. So it's down to maybe 0.1% power. But still, at a megawatt or two, eventually you will start melting. And you could have a Zerk water reaction. If there's some water puddling around, steam could form. So you could have a Zerk water reaction. So you might get a fire of some sort. Or you might melt the boral plates away and they go away. But then how would you get water in there? Well, maybe they try to fill it back up. So you better use borated water. Or otherwise you might drive. So you could have a criticality if you don't do the prudent thing, which is if you're going to fill that pool up, maybe you think about borated water. And maybe you should fill it up with concrete. But you better use borated concrete also. So I'm sure, and this is not my province either. This is something that crit safety people that do this stuff for a living, and I'm sure they're looking at this. There's no doubt about it. They're looking at what are the options and what can we do. The problem is we don't know what's going on. You can't get people close to this place. But if recriticality occurs, things get worse a lot. I don't think it's, from what I can tell, you can't rule it out, but I think it's highly unlikely. But if it were, you would get neutron production. That complicates life a lot. Increased heat generation in the fuel. We've been banking on the fact that we only worried about decay heat at 0.1% power. Well, you go critical, the power level goes up. So now we've got to wait again. And you will boil away the water, which actually will help you from the standpoint of criticality, but you may do some damage in the meantime. So filling with borated water may be a prudent thing to do. If it boils away, at least the boron's left behind. So they may be using borated water. I don't know. If they are, that's the prudent thing. They borated seawater that was injected into reactors 1, 2, and 3. That's the prudent thing to do. I think it's highly unlikely of a recriticality. There are some strange, narrow circumstances where you can say, well, this is possible. They just simply remove that by being prudent and adding boron to the water. So I'm guessing that this is well thought out, or people are thinking about it, and they'll do the prudent thing if they can. This may be, okay, severity. The spent pool fuels are open to the atmosphere. There's no motive force, though, to drive fission products. But you know, if you get recriticality, things get dicey. So, but at least at this point, if you can just simply keep, at this point, there is no burning graphite to drive this. So right now, we're not anywhere close to that. I think it's moving away from a TMI scale accident towards, but I think still distant from Chernobyl. Chernobyl was truly awful. Getting the pools in a stable configuration would help to keep this in the direction of 3 Mile Island severity.
Well, just a couple comments with regards to recriticality. In the BWR fuel assembly, there's a shroud around the fuel assembly, and so that really constrains the geometries that we can realize in here until the fuel gets to the point that it melts the stainless steel fitting at the bottom of it. So I would say there's constraints on geometry. And then there's this question of incorporating boron into the seawater when it's injected. Seawater turns out to be about 10,000 ppm sodium chloride. And the sodium has a non-zero cross-section, but the one that's the real winner of the day is chlorine 35 with a 45 barn cross-section. So if you've got something at 45 barns and 10,000 ppm, multiply those together and you get 450,000 barn ppm. The cross-section for boron is about 3,500 barns. So what that means if you sit down with the back of the envelope is that as long as they're injecting seawater, they're effectively injecting water that's 100 ppm boron. And so in terms of criticality, you know, the worst thing they could do is inject pure water. They don't have any pure water, and so they're injecting what's easy, which is seawater. And it turns out that seawater inherently has some criticality control. Not that it's designed in, but just as a matter of the fact that it contains chlorine. So just a couple comments.
Thanks, Mike.
I'd like to also add a couple more comments that I did not have time to get to in my presentation earlier. One has to do with maybe a question that was raised somewhat a while ago. And that is, we have cesium and iodine and so on released, but they do not necessarily escape from reactor structures so readily, because often they are not released in elemental forms, not iodine and cesium. They form cesium hydroxide, cesium iodide, which are typically in colloidal forms. They played out on any cold surfaces they run into inside the reactor building structures and so on. That's one of the lessons we learned from the accident at 3 Mile Island. There were quite a bit of cesium and iodine release, but the actual amount of cesium iodine release to the atmosphere was much less. So we had to struggle and try to find out why there was not so much of cesium iodine released, although there was a lot of that, those gases released into the reactor building. Okay, that's one point I'd like to make. So even in this terrible episode going on, evolving in Japan, the actual releases would be reduced by a significant amount. Second point I'd like to make is, after the 3 Mile Island accident, quite a bit of study was performed about the strengths of reactor pressure vessels. And my best educated estimate is pressure vessels are strong structures. And pressure vessels would be able to withstand explosive force-associated several hundred pounds of TNT, something that knocked off the Oklahoma City government building in the terrible terrorist bombing of Oklahoma City several years ago. That was a horrific explosion, some of you remember. So the inherent strengths of reactor vessel should be considered so that we do not have to be unnecessarily worried about breach of the reactor vessel and following sequence of events that some people talked about as China syndrome.
All right. I wanted to put some of the dose numbers that we have been hearing on the news as well as seeing confirmed in reports into a little bit of perspective. But I wanted to preface my remarks by saying at this point it is premature to do a public health risk assessment because the event is not over. We do not know the releases from the incident because the incident is not over. We do not know the worker doses because the situation is still evolving. So with that, I'd like to put some of the numbers in perspective for you. Here is the average dose to the US population per year. You're getting 620 millirem per year. And of that, 320 is from medical procedures. That's averaged across the population. There are procedures such as high-dose CT that might be 1,000 millirem. So those individuals would get 1,000 millirem doses. They're contributing to the overall average. The average natural background is 300 millirem. That is an average with the larger numbers discarded from the average. If you go back and read the National Council on Radiation Protection report that number comes from, they threw out all the high background numbers. The background varies by a factor of 10, and they didn't want to bias their numbers, so they threw out some of the very high numbers. Of that 300, 200 of that is due to radon gas in homes, and that can vary by an order of magnitude depending on where your home is. This is simply an average. And the difference in your average natural background, this 100 millirem, which was the 300 minus the 200, that is caused from between living at sea level versus living in Denver is about 100. That's because at a higher elevation, there's less atmosphere to shield you from cosmic rays. So the public limit is 100 millirem per year, which is roughly equivalent to the difference in natural background radiation between sea level and living up in the Rocky Mountains. So this is very conservative. The evacuation zones, where they say we're having an incident and they have an emergency plan and something's going on in a nuclear plant, the distance of those zones are designed so that the public will not exceed its 100 millirem limit. These are all, the concern for lower doses is cancer and some genetic defects. They're all statistical effects. How do we know there's been a radiation cancer-induced? They're all calculated. We cannot tell the difference between a radiation-induced cancer and a naturally occurring cancer because about 20 to 25% of the population will get cancer. A number from Beer 7, roughly, and I've rounded it so you can remember it or use it quickly, is that 10,000 millirem, which is there, gives you roughly a 0.5% increase in cancer risk. Now, below 10,000 milligram, there's another problem here, is that the cancer risks are so small that it's impossible epidemiologically to tell what the relationship between the dose and the risk is. And there was a very nice article in Science by one of the directors of the National Institutes of Health about that. It's impossible to know. For convenience, we assume that that relationship is linear. But for all practical purpose, our lowest data point from the Hiroshima and Nagasaki survivors was at 10,000 millirem. We really don't know what goes on below that amount. So that should put in perspective the low dose numbers. Now, let's see what's going on with the public. There have been clouds that rapidly disperse or dilute themselves with distance. And that's one reason why evacuation is a good thing if you're trying to get the doses to the public as low as they can possibly be. The other thing is, at the edge of the plant boundaries, you may have high dose rates if you had unusual things going on in the plant, such as fuel that was in a spent fuel pool and it was no longer covered on the top with water. So you want to get people far away. You don't always move people. If there's a cloud passing over that's radioactive, sheltering in place may be a wiser decision in terms of reducing public doses. So Tokyo, they said it was 10 times background, which was an unconfirmed report. And it was unconfirmed for a very short time period. Probably in Tokyo, there was a cloud that was simply passing over. So it was a very short time period. But let's assume that that persisted for 10 days and the person stood in that spot for 10 days. I calculate that it's roughly the difference between living in Tokyo and Denver for 1 year. So that's why I feel very comfortable saying to the press, there has been no significant health effect on the people of Japan. So far, so good, unless I see another number. This is a confirmed report, which is a number which I like, which is 0.4. And for an unknown time, I said that's 14 times background. And if people were there for 10 days, because it took them 10 days to remove them, we're still back to a level that is insignificant. And again, we've got variations in background radiation across the planet that are factors of 5 to 10. So at this point, I'm not concerned about the general public. They're concerned about other things that happen later. What about Chernobyl, though? You've heard about Chernobyl, and there were induced cancers in the population. Childhood leukemia was observed. Well, Chernobyl, they did not evacuate the local population. So one thing that makes me feel a little bit better about the company, TEPCO, and the government is that they acted very quickly and responsibly to put into place their prearranged evacuation plans. How would we minimize public dose, which brings up another Chernobyl issue? There are things that will be put into place to protect the population. We've already seen evacuation and sheltering in place. Evacuation zones can also be increased. Screening and decontamination. At this point, you may see clippings on TV where they're have detectors and they're checking people for contamination coming out. Well, that's a very good thing to do. There was an accident in Guyana where they had a cesium source from a medical facility, and it was a huge mess, and they took 100,000 people into a football stadium, and they scanned every single one of them, and it really calmed people down, and they made sure there wasn't somebody who was radioactive. So this is very good from the viewpoint of keeping people happy and making sure there's not something going on that we don't know about. Minimize consumption of contaminated water and foodstuffs. This comes later. We don't know. There have been releases or will be releases. There were 6,000 thyroid cancers as a result of Chernobyl. Nearly all of them were preventable. Do not let children drink contaminated milk. That would have prevented those problems. Well, what about potassium iodide? You know, I've got some potassium iodide to sell you. Potassium, meet me out back. Potassium, the thyroid is like a cup, and it slurps up, or like a sponge, and it slurps up iodine, whether it's radioactive or stable, and it slurps up iodine. Half the iodine you consume goes to your thyroid and sticks there for a while and exposes your thyroid, so you get a pretty high thyroid dose if it's radioactive. But if you fill up that cup or sponge with non-radioactive iodine, then radioactive iodine can't get in there and is excreted rapidly from the body. That's how it works. So sometimes they will give a worker who's got to go into an environment some kind of iodine tablet. Why shouldn't you buy my potassium iodide tablets? There are a lot of people who have iodine allergies, and this could cause you serious illness. And it's not going to necessarily help because it's the cows that are eating the grass that are concentrating the iodine in the milk, which is what is causing the dose to be high. So this is something we're going to have to worry about when this is over, if there are significant releases. And longer-term monitoring of environmental contamination. There's a 30-kilometer non-occupiable zone around Chernobyl. People were displaced, and that's not trivial. At the current time, we don't know what's happened, so we can't assess that. We would need detectors to go in and quickly evaluate that, evaluate hotspots, evaluate radiation levels in the plant. I'm looking for Professor He to help us out in that regard. What about the workers, though? The workers I worry more about, and here's why. Skin burns happen about 3,000 rad. I did switch units on purpose. The units being used in the press and by TEPCO are incorrect. High-level doses should be in these units, but you'll have to take my class to understand that. Anyway, there's skin burns at 3,000 rads, central nervous system at 1,000, GI tract, male sterility, and so on. If you get to 500 rad all at once exposure, then that's serious, and 50% of the people will die within 30 days. But before you can see any of these high dose effects, you have to have at least 100 rad. These doses are these effects are different from cancers. You do not get these effects unless you exceed a number, a threshold. So as long as you're below the threshold, you do not see the effect. And so below 100, you would see none of these effects for sure. Okay? The 100 is a very survivable number. The other thing is the severity of the effect. It depends upon the dose. The blood, GI tract, and central nervous system, that is part of a syndrome called acute radiation syndrome, and you may hear it called radiation sickness. Okay, so here we go. Whereas our US worker limit is 5. And everyone's making a big deal about the US worker limit. The limit for normal operations is 5. The international limit is 2. But it's up to 5 or more as long as you don't exceed 10 in 5 years. So they actually can go 10 if they've got a weird situation going on, which we do. So, but if there's an emergency situation where you're trying to prevent massive damage to equipment, or you're trying to prevent releases from the site boundary, there's an international standard, and it's in force here in the United States, which is 25 rem. With all the news that was circulating, oh my gosh, they are now 5 times the US limit for radiation worker exposure, that was reassuring to me. Because what it said was TEPCO was being responsible. They said, unlike the Russians, they said the international standard is 25, and we are now going to our emergency mode for worker exposure controls of 25, and we're going to try to keep all the workers below 25. And look at this. That's a factor of 4 margin before they get into any high dose effects. Now, there's a probability that these workers now, because that's above 10 for low dose effects, there's a probability of 2% that they might get cancers later. So they are very, very dedicated individuals. There was one confirmed report of a worker getting 11. The deaths by acute radiation syndrome of workers at this plant are not confirmed, so I would say they are greatly exaggerated. At Chernobyl, there were 28 acute radiation syndrome deaths. They did not say we're going to keep everybody's doses below 25. There was also another about 18 or 19 deaths caused by skin burns, which were also likely preventable. If we're going to say that we're going to stick with a limit, in rush the radiation safety white hats, and they're going to have procedures and processes to try to keep the doses to the workers lower than this amount. Here's what they have been contending with, though. These are doses as a function of time, and they're nice, and then they jump up to 1 hour an hour for 5 hours at the plant boundary. So these events and these spikes in radiation dose are corresponding to things that are happening in the plant. And so from the viewpoint of controlling worker exposure, they're going to have to be responding and backing people off from areas that are doing particular jobs. So this whole thing that went around that all 50 workers have abandoned the site, Then this was, no, it turned out that wasn't true. That might have had something to do with having to abandon a particular operation because something spiked high, so they backed off and then apologized. That's what it seemed like when I watched the announcement from TEPCO, that they had stopped doing something because a radiation level had jumped up. So what are the higher level dose rates that we have seen reported? And these come from TEPCO or IAEA, except for this 10 times background in Tokyo. So here's the rad per hour, and I showed you that's limited impact, that's no impact. You were nowhere close to with some of these reports that were coming in, anything that would give you acute radiation syndrome or anything unless you stood in that spot and the dose remained high, which it isn't, for a very long time. Main gate block 4 explosion, the report on that last slide, that peak was 5 hours. It's 6 rad, so if you were dumb and you had your radiation detector there and you stood there for 5 hours, you would have gotten 6 rad. So you would have been in trouble if you worked at Fermi because that's more than the occupational limit for a year. But you're still within 25, but you're still pretty dumb because you didn't follow good radiation protection practice. Outside Unit 3, this is the biggest number that I have seen, and I don't know how long it lasted, which was 40 R per hour, 40 rad per hour. You could stay there for 40 minutes and still be at that 25 rad limit. Remember, 25 rad is a factor of 4 below that which you'd see any effect on your blood, and a factor of 20 below that that you would be risking your life. But we can manage worker doses, and that's the important thing. And I would hope that the Japanese are managing their worker doses. They have real-time radiation measurements from fixed detectors around the plant, as well as portable monitors, and they're trained to use them. Time, you can rotate workers, and you can take approaches that require less time. So if here's a really radioactive source, you can have one worker run up, run back, turn the knob a little, someone else run in, turn the knob a little more, have another worker run in and turn the knob, and you can reduce it. Distance is another way of protecting people. Poles, choice of methods that keep workers at a distance. Robotics. Hello, Professor Weehee. This is for later, okay? Shielding, light protective clothing for the betas. That you have those white suits on, you get betas on you, you take them off, your exposure's gone. Later, you would have additions of shielding. Apparently, the Washington Post did not understand that if you had fuel rods and suddenly they were uncovered from water on the top or otherwise, the water is also a tremendous shield. So fluctuations in water would be causing fluctuations if you wanted to go that way in doses that we're seeing. Contamination control. How do you do contamination control? You simply can have clothing that you can discard over your regular clothing, soap and water, and intake control respirators, and stay time in areas that have high doses. Thank you.
Professor Annalisa Manera.
Well, you. Okay, what I would like to talk about is actually
the improvement in existing reactors that have been already done to minimize the impact of so-called beyond design basis accident or severe accident, actually what happened in Fukushima. So first of all is in many reactors there are squib valves, so-called fail-safe valves, which have been installed, for example, on the RPV steam line, because what happened in Fukushima is that once the accident took place, the safety relief valve went open so that you could depressurize the reactor pressure vessel. And you want to do that because so you can inject the emergency water into the reactor. And to do that, the pressure has to go low. But what happened in Fukushima is that after they lost the power and also the diesel generators, the valve which they had installed on the RPV, they got closed because they were powered by some additional batteries, and once these batteries were expired in something like 5 hours, these valves reclosed, and so the reactor pressure vessel started to pressurize again, which was really bad. So in existing plants, unfortunately not in Fukushima, these squib valves are installed, and these valves actually, they do not close once they have been opened. Other safety features which are available at existing plants is redundant emergency diesel rooms, which are, however, spatially separated so that if one room gets damaged, it is not necessarily that the next room is also damaged, and so this would have helped. Also, okay, there are several improved measurements against hydrogen explosion, and we still have to find out why igniters did not work in Fukushima. But there are actually several studies that also says, okay, you need igniters, but it's also important where these igniters are located. If they are not located in the right place, they might not serve their function. And so maybe something like this happened in Fukushima. We do not know. We will have to see. Then another important feature is the fact that as the evolution of the design went on, larger and larger containment volumes have been used. So we have to say that Fukushima, especially, well, most of the Fukushima units, they use a so-called Mark I containment, which is really the generation 1 of the containment designed by GE, which is pretty small, and therefore it has lower thermal capacity with respect to the newer generation containment. For example, I mean, if you take the Mark III containment, the pressure suppressor pool can withstand more than 24 hours without cooling. This was not the case at Fukushima 1. Other features that have been even installed in existing plant, even of the type of Fukushima 1, but unfortunately not a Fukushima 1, is the locating pools outside of the containment, because of course you cannot modify the containment, but nevertheless, I mean, locating pool in a higher location so that you can by gravity you can flood your containment even when you do not have electricity. And then, of course, the new design, they include a lot of passive features for cooling of the containment, and even basaltic concrete or so-called core catcher to catch eventually the corium if you have a full melting of the core and even the rupture of the RPV of the reactor pressure vessel. And then you have passive systems for cooling the corium inside the containment. So, and here, just to show a picture, is the evolution actually of containment from Mark I to Mark II, Mark III, and this is the latest containment of the advanced boiling water reactor. So they are all General Electric design. Unfortunately, I mean, we were dealing now with a reactor which is pretty old, and ironically, I mean, Fukushima 1, the unit 1, was actually planned to be shut down for good at the end of this month. So it's very, 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 very bad luck. Now I would like actually to give a very short overview of the new design, which include several passive systems, not only for the cooling of the containment, but also for the cooling of the primary system, so the RPV, in case, and this means that all these systems will work even in case you would have a full loss of electricity like it happened in Fukushima. For example, if you look at the ESBWR, which is a design by General Electric, it has actually, and here you see the RPV, this is the primary containment, this is a pool in the secondary containment, and okay, above here you will have the secondary containment walls. what you see is that actually you have several systems for the cooling of the RPV, so the reactor pressure vessel. For example, you have this emergency condenser. They will come into action if you have high pressure in the RPV, or if you have a decrease of water level in the RPV. And what this does is actually cools the steam from the RPV, and it puts it then back down into the reactor so that you do not have a loss of inventory. And what it does, it removes energy from the reactor pressure vessel, so you have a depressurization of the reactor pressure vessel without need of any electricity. Then you have the containment cooling. What this does is actually it's also passive. So if the pressure in the containment start increasing because you, like it happened in Fukushima, you would release some steam from the safety relief valve into the primary containment. What will system does is that if the pressure here increases, the air will be pressed inside this emergency condenser, and it will actually cool, help removing energy from the primary containment, so reducing actually the pressure in the primary containment passively. What you also have is this gravity-driven pool, which is also connected to the RPV, and it is connected also to the primary containment. So what you can do here is by opening some valves, which are opened just by some pyrotechnic technique. So again, no electricity. It's just a battery which is installed here. What this valve do will, once they open, they can flood the reactor or they can flood the primary containment. Similar system you have in the other boiling water reactor, which is named Kerina, and it is actually designed by Arriva, so this is a European company. But they have very similar systems. So you have an emergency condenser that is helping cooling the reactor pressure vessel in case of a loss of coolant, and you have a passive cooling for helping keeping the pressure and the temperature down in the primary containment. I will not go too much into details, but what I want to say is that you have, again, a series of passive systems also for pressurized water design. So what I showed before, they were all boiling water design, like in the case of Fukushima. But you have also passive systems designed for equivalent of pressurized water reactor. So this is for the cooling of the primary side, and the cooling of the containment is done by designing the containment geometry in such a way that you can have natural circulation between the containment parts. And then you have a very large pool at the top of the containment that by activation, a valve can be opened and the water can be used to cool the primary containment from the outside shell. And I would like to conclude with the last slide. So what I have here is actually the latest reactor design, or some of the latest reactor design. The advanced boiling water reactor is already existing. It's operating since '96. Several units are operating in Japan and some in Taiwan, or they are actually going to be in operation in Taiwan. And the EPR, there are 2 units